Hi, everyone. I think that after what we've saw with Orion, the amazing things that we can do with text, I can skip a few of my first slides that were supposed to convince you that we can do amazing things with text. So yeah, in this slide, I was supposed to tell you about the amazing progress that we had with generative models that are conditioned with text, but we'll skip a bit. Okay. But I think it's actually very related to the question that was asked here. Something that I asked myself in the last year is if natural language is sufficient for controlling visual creation. I think that nowadays we're used to control images and videos that we're generating with text, but I'm sure that all of you, that it happened to all of you, that you wanted something very specific, and it was very hard to achieve it with the current tools that we have that are conditioned with text. So let me show you an example. So let's say that we have this man. I hope that I don't hide. So let's say that we have this man, and I want to add him freckles. So with Nano Banana, this is the result that I will get, which looks very nice. But what if I want to have slightly less freckles? So I can ask Nano Banana to give slightly less, and it removes almost everything, which is not what I meant to achieve. I wanted to have only slightly less freckles. So I said, you remove too much, please add a bit more. And then I get more freckles than what I had at the beginning. So never mind. So in this talk, I'm going to show you other approaches for controlling visual creation. And specifically, I think that for this task of controlling the strengths of an edit, a much more intuitive controller could be a slider, like we see here. Let's say that we want to make the jacket more fluffy. We can tune the exact strength that we want for this edit. And I think that the question that was raised up earlier about preserving the identity in the style edits that we saw with Lucy is very, very related to that. Okay, so ideally we would like to be able to navigate over different results with different strengths of the edit. Okay, so why can't we just train? We have great models today. Why can't we just train the model to be conditioned on a scalar that will specify the edit strengths that we would like to have? So as in many problems that we have, the main issue is the data. Achieving data for paired data for image editing or video editing is very difficult, like I'm sure that also Descartes knows very well. But for achieving data for different scales of an edit is even more difficult, and of course that it does not exist in the wild. So I will, in the work that I'm going to talk about, I will explore two approaches. One is one type of approaches that I'm talking to talk about are training-free approaches that do not require any supervision. And then we will see how we can use this training-free approach to generate data and finally fine-tune an existing image editing model to be conditioned on editing strengths. Okay, so a quick recap about diffusion models. Orianos already gave a great introduction, but for those of you who missed that, so a diffusion model is a generative model that generates an image or a video by iteratively denoising a Gaussian noise. So on the left, you can see that we start from sampling a Gaussian noise, and the model was trained to denoise this noisy image until we get to the final clean image. And most of the state-of-the-art diffusion models that we have today are actually conditional diffusion models, which means that the model receives as input not only the noisy image, but also a condition, which can be, for example, a text prompt. So you can see in this figure that the model is drawn as a unit, but nowadays everyone is using transformers. So actually both the noisy image and the text prompts are inputted into the model as a long sequence of tokens. And Something that was very advanced in the last year are image editing and even video editing diffusion models, in which the model is conditioned not only on the noisy image and the text prompt, but also on a source image or a source video that we would like to generate. So for example, here, we would like to take this white flower and turn it into a sunflower. So the model receives as input a Gaussian noise, which will eventually be the edited image, the text prompt that describes the edit, and the source image. And the noise image until we get the sunflower. Okay, so let's see how we can take such a model, either text-to-image model or image editing model, and add this strength input. And we will start from one training-free approach. So our setting is a text-to-image diffusion transformer, which receives as input a noisy image and a text prompt, and outputs the noise that should be subtracted from the image. And what we ask in the work that I'm now going to present is whether we can manipulate the text embedding so that we will be able to tune this editing strength. And more specifically, the text prompt, I said that it is inputted into the model as a sequence of tokens, but how do we achieve this sequence of tokens? So the text prompt is, first of all, inputted into a text encoder, which gives us this sequence of tokens. And what we specifically what we asked in this work is, can we find editing direction in the text space and use them to control the strengths of the edit? And what do I mean by such editing directions? So what I would ideally want to find is a sequence of token, which I'm going to call direction, so that I can add them to the prompt that describes the edit or the generation, multiply this new set of tokens, the blue ones, with a scalar alpha that describes the editing strength, and this will be the controller for the editing strength. So let's see how we can find such a direction. So I'm sure that all of you know the concept of autoencoder, which gets as input a vector, compresses it into some latent space, and then decodes it. An autoencoder is usually trained with a reconstruction objective. And what our approach in this work was to look at sparse autoencoders. So sparse autoencoders are very similar to autoencoders in the sense that they reconstruct a vector. But the difference is that a sparse autoencoder, instead of compressing the latent vector, it actually increases the dimension and maps a given vector into some more high dimensional space, as you can see here. So I think in the first time that you see it, it's a bit confusing that the encoder is drawn as we usually draw a decoder and vice versa. And why did we look at this sparse autoencoder and how can they be useful? So the main idea is that the latent space that is produced by such sparse autoencoders is sparse, and therefore different attributes are typically disentangled. So different aspects about the image or about here the text are going to be represented by different entries, by different dimensions in this sparse vector. So now let's see how we use this sparse autoencoder to find the editing directions in the text space. Yeah, so specifically we train the sparse autoencoder on text tokens produced by the text encoder. Okay, so let's see how do we find the direction. So let's say, for example, that our goal is to perform an edit of making a person more happy. So we will start from two prompts, a prompt man something and happy man with some description. We're going to encode each of these prompts into the text space, and then lift them into the sparse latent space. So now for each of these prompts, we have sparse representation in our latent space. Now, ideally, what maybe you would think that we would like to do is to subtract between the representation of the happy man and the representation of the man. But the issue is that as you can also see in the figure, for each of these prompts, we have different number of tokens that represent it. So directly subtracting between them is not really possible. So what we do is max pooling each of these. The max pool is over the number of tokens, and this gives us a single sparse vector for each of these prompts. The reason that such a pooling works is because the space is sparse. So even if we take max over different vectors, we don't override the important attributes. And now once we have a single representation for each of these prompts, we can kind of subtract between them and find the entries that are responsible for the attribute that we added. For example, here they happy. And by using a mask that describes where the important entries and applying it on the representation of the edited prompt, we can find a direction that change the expression of a person to happy. So now let's see how we can use this direction to edit an image. But first of all, since we want to stabilize this process, we don't find the direction based on only a single pair of prompts. We apply the process from the previous slide on many pairs of prompts and apply PCA and find the principal component to have a more stabilized direction. So now we will see how we can edit with this direction. So let's say that we have this prompt, man sits in a bar, and we want to turn the man to be happy. So we encode with our text encoder the man sits in a bar, encode the text tokens into the sparse latent space, and apply the direction that we found specifically for the attribute of happy on the token that corresponds to the man, decode it back into the original text space, and input this representation into our diffusion model to get the edited image. So let's relax by seeing a few results. So by manipulating the alpha that this WT that controls the editing strength, we can control the blondness of the woman or how much mustache is added to this guy. איך אני עם זמנים? מה שם? So. Okay, and actually we trained our sparse autoencoders only on only on prompts that are related to humans, but it turns out that it also works on other prompts, so we can make this tree blooming or turn this sword to be rusty, and again control the strength of this edit, something that would be much more difficult to do only with text, only with natural language. Okay, now I will turn to talk about another work, which is again training free and does basically the same thing of controlling the editing strength. One limitation of the previous work is that we need to train the sparse autoencoder. It doesn't need supervision specifically for the task of editing, but still we need to train something. So now we will see something that is completely training free. And specifically, we explore the use of CFG or classifier free guidance for controlling the editing strength. So first of all, what is CFG for those of you who are not familiar with it? So something that was not accurate when I told you about how does the diffusion model work is that we don't directly use the conditional prediction of the model to denoise the noisy image. We denote here the model by epsilon. ZT is the noisy image and C is the condition. We actually use something called CFG prediction to denoise the image. And what it means is that in addition to the conditional prediction, we use unconditional prediction. Unconditional prediction means that we input an empty prompt. And we do this equation. We start from the unconditional prediction and extrapolate towards the direction between the conditional and unconditional prediction. And S is called the guidance scale. Why people use this CFG? To improve the prompt adherence, to improve the adherence to the condition. Let's look at it a bit more from a geometric perspective. So let's say that we are in time step T of the diffusion. So we are on the manifold PT. We are in the point ZT. And we want to denoise it. We want to reach this green manifold PT minus 1. So we apply the model 2 times on ZT, 1 time with the condition, with the text prompt, and 1 time with the empty prompt. And then, exactly as written there, we start from the unconditional prediction and extrapolate towards the conditional prediction. The guidance scale is typically larger than 1. It's typically around 4 or something like that. And since CFG was introduced to improve the prompt adherence, it is very natural to ask whether in editing model it can be used to control the edit strength, right? And we call just a terminology, so we call the point that we start from the CFG prediction the origin. Okay, now how does CFG looks like in image editing models? Exactly like in text condition models. The only difference is now the model is also conditioned on the reference image, on the input image, but we still have the guidance scale and the origin and everything. We will reformulate it a bit. Instead of calling the guidance scale S, let's write alpha, which is going to be a scalar from 0 to 1, which is the edit strength, and we will multiply it by some default guidance scale. Now, if you play with this alpha, if you generate images with different alphas between 0 and 1, you get these results, which are, I think, quite disappointing, right? Maybe on the alpha equals 1, it's pretty good. Here, it's also not bad. Here, the prompt is that we're supposed to add mask to the woman. But when we look at the results for the lower alphas, we got something that looks very weird. What would you expect maybe to have for alpha equals 0? The same image, exactly. But for some reason, it's not the case. So let's see why it happens. So to understand what's going on, why for this alpha equals 0 we get this weird result, we need to understand what is the meaning of this unconditional prediction. Also, people call it usually null prediction. So in text-to-image models, the way people train this unconditional prediction, during the training of the model, they take the empty prompt, they take a random image from the data set, and the goal is to generate this random image. So in text-to-image model, the unconditional prediction corresponds to any image. And with the same logic, in image editing model, what would the unconditional prediction mean? Yeah, I heard it. So any edit. Sometimes it's confusing, and the more intuitive thing to think about is that it actually corresponds to performing no edit, but it actually corresponds to any edit. And if we look again at the result that we got for alpha equals 0, we see that we just got a random edit. So what we propose to do in this work is something that we call adaptive origin guidance. And the idea is that in addition to the conditional and unconditional prediction, we are also going to use something that we call the identity prediction, which is just going to be a prompt that tells the model you should return the same the same image. And what are we doing with these three predictions? Basically, the origin is now determined according to the alpha strengths. According to alpha, so for alpha equals 0, the origin is completely in the identity prediction, and we still do the same extrapolation as in CFG. And as we increase alpha, the origin moves towards the unconditional prediction. So for alpha equals 0.2, we move a bit towards the unconditional prediction. For alpha equals 0.8, we're already very close to the unconditional prediction, and still we do the same extrapolation towards the CFG direction. So this is a bit more in equations, exactly what we see. So what we do, so the origin is interpolation between the identity prediction and the unconditional prediction, and we just plug it into the CFG equation. How do we obtain this identity prediction? So we found that in some models, this is something that already exists in the model. You can just tell it don't edit the image, but if it doesn't exist, you can just do a very small fine-tuning, very lightweight fine-tuning for the model to add a token that tells the model just don't edit the image. And these are the results that we get with this adaptive origin guidance. So now you can see that for alpha equals 0, we indeed get the input image. And as we increase alpha, we get a bigger mask on the woman. If you followed all the math, I'm sure that you have many questions around why not completely replacing the unconditional prediction with the identity prediction or many other formulations. I'm not going to talk about it here, but in the paper we explore also different variants and show why and explain why they don't work. Okay, so let's see some results. So for example, here we can start from this camel in the desert, change the sand into snow, add the northern lights, and know that everything is very gradual. Nothing in this method is specific to image editing. So it actually also works on video. So we can add hair to this man and control how much hair is added. Actually, this work was done by an intern in Descartes. So this is with the Lucy model. I'm not sure if Rian is still here. Okay. Now, another way to look at controlling the editing strengths is navigating over the trade-off between preservation of the input image or input video and adherence to the prompt that describes the edit. Now, in this example, when adding the hair, we don't really have a trade-off. We don't lose something when we use the maximal edit strength. But in other examples, you might have a trade-off. Let's say that I want to take an image of myself and turn myself into a pop figure. So you see on the left something that actually looks like pop figure, but if I would show you only this image, maybe you would not recognize that this is me. But here on the right, it doesn't really have the features of pop figure, but I think you can, at least I'm more recognizable here. So in the next work that I'm going to talk about, we looked at this task of controlling the editing strength as navigating on the trade-off between preservation and editing. And specifically, recently there are many methods for post-training diffusion models with some objective, which is quantified by a reward. And specifically in this case, we can set the rewards to be a reward that measures the preservation of the input image. and a reward that measures the edit, the adherence to the edit. And our goal is to navigate over these rewards. Now, the main issue with post-training methods for diffusion models is that they typically assume that you have a single scalar that describes the reward. And in this case, where you have a trade-off between the preservation of the image and the edit, you're stuck in just one scalar that can describe the trade-off between them. So in cases like this, where you have more than a single reward, it's not very clear what to do. So our main idea is to take such methods that are able to do reward-based post-training and add some preference vector that describes the trade-off that should be between the different rewards. So this is a vector where each entry is a scalar from 0 to 1, and all the scalars are summed to 1, and it gives us the trade-off that there should be between the rewards. I won't get into the technical details, but the idea is to condition the model, which we now call it a policy, on this vector and modify the method so that we will take it. The model will adhere not only to the prompt, but also to this preference vector. So these are some results. So we can take the corgi and change it to pixel art style. So you can see on the left that the image is preserved very well. We still see the pixel art style, but it doesn't have the usual feature of maybe the colorfulness of pixel art style. And on the right, we lost a bit the identity of the dog, but it looks much more like a pixel art style, and the same in the bottom example. We also quantify it and show that we are the best. And actually, this method is generic, and it's not only for the rewards that I mentioned. We can basically use it for any reward, for any set of rewards that you can think about. So on the top example, you can see that we fine-tune a model to be able to control between photorealism and sketch. And also here it works on videos. So again, we can control the edit between photorealism and anime. Okay, so I presented 3 approaches. All of them didn't require a lot of supervision, but all of them, maybe apart from the last one, they add some complication to the inference, right? In the first method, we had this process of finding the direction. In the second method, we have some overhead for the CFG. So something that we can do is to basically use these methods to generate data and finally distill it into an existing image editing model. So in this work that I will now briefly mention, this is exactly what we do. We generate data. We generate such sequences that correspond to different editing strengths, and then distill, take an existing image editing model, specifically flux context, and fine-tune it to accept as input this strength scalar. But basically, I will skip maybe the details, but feel free to check out the paper. Most of the paper is about how to inject it into the model. Here you can see some results. So we can open the panda's mouth, change the size of the car, add snow, change the jacket to be more fluffy. And again, in all these edits that I show, we control the strengths, and this enables much more fine-grained edit. So these are the papers that I mentioned. Some of the people that are written here are here in the audience, so feel free to catch them later and ask questions. Specifically, Sarah is here. Shelly, Ariel. Yeah, that's all. Thank you.